Okay, so this video is not going to be focused specifically on earthquakes. It's a more broad numerical tool, but we're starting to have a need to talk about this topic, and so it's worth spending a few minutes to discuss. So in this earthquake data, and we just seen it in the last video, there's a lot of data that deals with exponentials and logarithms, and there's a couple tips especially when we're looking at plotting of this data, that I think it's worth spending a few minutes on. When I first got into this business, it took me a while to get comfortable with the logarithms and the exponentials and log scaling of plots. And so I think spending a few minutes here will help probably preempt some confusion and about why we're doing this and how it works. So to get ourselves started here, we've got plots. Here on the left side is exponential functions. So I've got x on the horizontal axis. And then in blue, we have e to the x, and red is 10 to the x. So those are two exponential functions with a different base. E just being that constant, 2.7 something. So both of these, the blue and the red curve on the left, they're both increasing exponentially. So the slope of the function is getting bigger, and it's getting bigger in kind of a proportional rate as you move to the right. The rate of increase of that slope is different between the two functions. And then on the right, we've got logarithm functions. So the logarithm is just the inverse of the exponential. And so we've got a natural log, which is the inverse of the e to the x function. So if I take e to the x and then I take the natural log of e to the x, I'll get back x. And then the base 10 log is just the inverse function of the 10 to the x function. So here on the right, we can see that as x gets bigger, these functions are having decreasing slopes, and their slope is decreasing at a fixed rate. Okay, and so these are exponential logarithmic relationships, and they arise a lot in the seismic hazard and risk world. So we've already seen, for instance, that the moment magnitude is related to the moment by a natural log, and some scaling relationships are related by logarithms to predictor parameters. So when we have that situation where we've got these exponentials and logarithms, it makes a lot of sense to do log scaling on our plots. And so let's talk for a minute about what log scaled plots are, and then how we can get them as well. So the upper figure here, this is the linear scale plot. This is just the left figure from the previous slide. And you see these so often, you probably don't even think about it. But the linear scale plot, the idea is that equally spaced intervals on the plot corresponds to kind of equal differences in value. So 2 and 4 differ by 2, and 4 and 6 differ by 2. And they're spaced equally in this linear scale plot. Okay. In a log scale plot, the equal spacing is going to correspond to equal ratios rather than equal differences. All right, so maybe we can label a few points onto this plot. So I've got 2, 3, 4, 5, and 6. So we can see here with this log scaling that 4 and 6 are closer together than 2 and 4 are. So we don't maintain that equal spacing from the linear case. Instead, let's go up a couple more. I'm going to go up to 8. And if we look at the distance between 2 and 4 and the distance between 4 and 8, those are equal. So changing by a factor of 2 in value is going to correspond to equally spaced intervals on a log scale plot. All right. And the interesting thing about these log scale plots is these exponential functions. So the top plot and the bottom plot are plotting the same functions. But when I plot these exponential functions in log scale, they look linear. All right, so my blue line and my red line are now linear, and they just have different slopes to them. All right. Our eyes are really good at looking at linear relationships. Lots of things like linear regression work on linear relationships. And so this log transformation can get us back to linear relationships visually in the same way that taking a logarithm can get us back to linear relationships with these exponential functions. Okay, so that's why these log scales are really valuable. And we'll talk about that a little bit more moving forward. So on the left-hand side here, I've got 4 plots. The left-hand side, I've got the exponential functions. That was the e to the x and the 10 to the x. And when that's the case, making a log-scaled y-axis is the transformation that gets us to this linear behavior. Right? So that's what we saw in the previous slide. On the right, we have the logarithmic functions. And in that case, what will get us to linear behavior is taking a log-scaled x-axis. Okay? So whether we're dealing with exponentials or logarithms, the log scaling will kind of linearize our patterns. So we can flip one of the axes. Sometimes we actually flip both axes to log scale as well, and that's fine. Actually, maybe speaking of flipping the axes, why don't we back up one slide and let's talk for one more second about flipping axes on this slide. So just some computer help here. So these types of scaled plots are really easy to do in our computer. So with MATLAB, all you have to do is give it the commands semi log y and give it the x data and the y data, and it'll make a plot like the bottom figure where it's put the y-axis into log scale. Similarly, there's a semi-log x function, which is what we need in the next slide. Or if you want to put both axes into log scale, you can use the command log xy. Okay. And similarly in Python, that's the library for plotting, you can use, if PLT is kind of the name you pulled in that package, you can do PLT semi-log y, x and y, or PLT log xy. So pretty much the same convention. So those are easy ways to just flip your axes to the scale you need. Okay, and we talked about why to do this. So let's go back to some data to try to connect this to the earlier content. So when we have data like in this scaling relationship, so let's take a look at that. So the circles on these plots are the data from that Wells and Coppersmith model that was discussed in the previous video. Here on the left side, we've got each circle is an earthquake. The x-axis shows the rupture length of the earthquake, and the y-axis shows the magnitude of the earthquake. And we've got this kind of funny relationship where the magnitude is increasing quickly with rupture length on the left, and then it kind of flattens out on the right part of the plot. If we just take a logarithm of the x-axis, we can make this plot on the right, where now the data has a really rather linear relationship, and I had already drawn in the line there, so we can put some sort of a linear relationship between the log of rupture length and magnitude. And that was kind of the functional form we discussed previously. So that's a nice clean transformation that gets us linear. The problem here is that the units on the x-axis are incomprehensible. So I don't know what log rupture length of 3, what that means physically, because the log transformation has kind of removed my units. So there's a couple ways we can handle this data, and you can see two plots here that visually look the same. On the left side, I've got log rupture length on the horizontal axis. So we could get this in our computer program if we wanted to, say, plot, and then we plotted the log of the x data we were interested in versus the y data. So we would just take the log of the data before we even plotted it, and it's going to show up something like the left. Alternatively, on the right-hand side, we could do a plot where we use semi-log x, and then we just pass in the raw values, x and y. Okay, so in this case, the x-axis is still rupture length, non-log, but we've log scaled the plot so that the spacing is not linear with differences anymore, it's linear with ratios. And we get the same visual pattern, but the horizontal axis is now interpretable. So if I want to guess what's the magnitude associated with a rupture length of 30 kilometers, I can go find 30 kilometers here, map up into the data very easily. So we get the benefit of working in the units we're comfortable with, but we get also the benefit of the log scaling. And so that's a really nice way to look at this data. Just to highlight the differences, in the right case, we're passing in the raw data by itself. In the left case, we're taking the log of the data before we ask the computer to plot it for us. And so we're using the semi-log on the right-hand side to do the job of the logarithm that we took ourselves on the left-hand side. Log scaling is helpful when we have log normal distributions. The log normal distribution is one where the of the data is normally distributed. And so the log transformation helps us a lot with these visuals. So again, here on the left and right, it's the same set of data. So we've got earthquakes with magnitudes and rupture lengths, and this kind of nonlinear trend on the left-hand side, the red line being kind of a mean trend from like a Wells and Coppersmith model. And we say that the rupture are normally distributed, so I've got some log normal distributions superimposed here as well. On the right-hand side, we just made a semi-log y plot. And so we did this transformation that gets us to the linear trends. And those log normal distributions on the left, when the vertical axis gets log scaled, they turn into normal distributions. So we've got linear trends and normal distributions, which are lots easier to work with. To push this a little more, so I've got the same figure on the left. We've got the linear scaled kind of logarithm of the y-axis values plotted. And so if we've got these kind of scaling relationships, so on the bottom, I've got an example model where the log of the rupture length is a linear function of magnitude, and then the standard deviation of the log of the length is a constant. So that's the red line and the distributions plotted up on the figures. These are the types of relationships that come out of the Wells and Coppersmith model. And if I've got a mean and the standard deviation of the log rupture length, and I want to compute a probability that a rupture length is bigger than, some value. So let's say I want it to be bigger than like 150 kilometers given a magnitude 7.5 earthquake. So I'm interested in kind of the distribution up in the top of that, or the probability in the top of that distribution. So this is the log normal distribution. And just to look at our bottom equation here, this is using the CDF for the log normal distribution, where we use the mean and the standard deviation of the log of the variable, and we take a log of the number we're interested in. Right, so there's log transformations all over in this thing, and that's consistent with the log transformation in our plot that we're making as well. So these log scaling is a kind of a natural analog with log distributions is the point. In this calculation in the bottom, we're using the mean and the standard deviation of the log length. Numerically, we're kind of looking over at this left-hand figure, but for our interpretation, the right-hand figure is visually equivalent, and we can kind of see how the same things are happening over there. And so the log scaling helps us to just see what's going on a little bit more intuitively. Okay, so that's kind of a quick look at log scaled plots, and we're going to look at so many log scaled plots in this field that I thought it was worth spending a few minutes just talking through, and maybe a little bit of a remedial background of like what log scaling is and why we do it. I suspect for many of you it's helpful to spend a few minutes just thinking about this, and you'll be a little more comfortable once you see those plots moving forward. So I hope that's helpful as just general background context.